Right. I welcome every one of us to Math 110, Lecture 4 and Lecture 5. And Lecture 4, which is indices and logarithm, while Lecture 5 is series and sequence. So I will be doing the combination of the two lectures and the, and the explanation of the two lectures in this very video. Now, for before I continue the class, I would like to inform that we've concluded all of the solutions to the exercises, to all of the exercises in the Math 110 manual. So for those of us that want to get all of the detailed questions, solutions, and answers to all of the exercises that we have there, you can message me via through my WhatsApp number, which I'll be dropping in the comment section. Thank you. So quickly, let's move to the course indices. Indices is, I believe, 90% of the students that are coming across this video must have one way or the other heard of indices. So it is a very common topic. Indices and logarithm is a very common and popular topic for those students that are familiar with mathematics. So let's quickly move to the rules. We have three rules that are stated here. So you have three rules, though we have a lot of rules, but these are the breakdown of the rules according to Math 110 manual. So rule 1 is q raised to power m multiplied by q raised to power n, which is the same thing as q raised to power m plus n. Rule 2 is q raised to power m divided by q raised to power n, which is q raised to power n minus n. Rule 3 is q raised to power n multiplied by qn, which is equals to qmn. So I believe this is explicit enough. The last rule that we have is called the reciprocal rule, which is 1 over q raised to power n, which is the same thing as q raised to power minus n. So if I give you 1 over 2 raised to power 3, you can still write it as 2 raised to power minus 3. So that's the breakdown of the reciprocal powers. Now we have an example, and this example, you notice that we have three things, that we have 8, we have 27, and 64. Now these three numbers that we have something similar, and their similarity is that they all have raised to the power of 3. So 3 raised to the power 3 is 8, 3 raised to the power 3 is 27, 4 raised to the power 3 is 64. And in order for further simplification, you take out all of the powers, which is 3. So by taking all of the powers out, we are left with 2 raised to the power 2 multiplied by 3 over 4, and our final answer is 3. So rules of logarithm. So as we have rules of indices, we have similar rules that are related to logarithm as well. So as you can see, we have 4 different rules, though we have more than 4 rules. We have more than 4 rules, but we are doing things based with respect to your manual. So the first rule, you have log m to the base of a is equals to n. Now the n that we are equating it to is a value that we decide to pick. So you can decide to pick any variable of your choice. Any variable of your choice. So this implies that, so the implication of this is that if you equate the logarithm to any variable of your choice, then the base of the logarithm can now take up the power that you equated it, can take up the variable that you equated it to as a power, such that you have a raised to power n is equals to m. So that's rule 1. Rule 2 is about multiplication. So multiplication in terms of addition, when you open the bracket, you have two different additions, right? Now this is not limited to only 2 variables. You can have 3 variables. You can have logarithm x multiplied by logarithm y multiplied by logarithm z. Are you getting me? And this is only applicable if and only if that the base of the logarithm are the same. So you get to understand this better. So the same thing goes for the division part. So division is negative. Now the last one, if you notice that the last one is having a power, the last one is actually more likely like rule 1, but it has a different case. So if you have logarithm of x to the base of a raised to the power of m equals to m log x base a. So what they did here is that they brought the power of m to the other side. Are you getting me? So they took the power of m to the other side. Then we have m log x base a. So that's the last. So you'll be seeing the application of this and in exam in other examples that will be coming across. So we have example 1, logarithm 9 base 3. So you can use 2 different rules to solve this. So by mere observation, for those of us that are very smart, you would have gotten the answer by using a faster approach. Since you have 9, you can write 9 as 3 raised to power 2, and you take 2 to the other side. So you have 2 log 3 base 3. 2 log 3 base 3 will give you 1. Now there is a rule that was not indicated in the rules, which you must know, and it is the rule. This rule is that whenever you have a logarithm that has the same value as the base, then the logarithm is equals to 1. So that's the first method to solve that. So that 9 that you have, you can write it as 3 raised to power 2, such that by the application of rule 4, you are going to have 2 log 3 base 3. And what's log 3 base 3? Log 3 base 3 is 1, and 2 times 1 is 2. So the answer for that logarithm is 2. But if you decide to use rule 1, according to rule 1 says that you are going to equate the logarithm to a particular variable of your choice. So by equating it to a particular variable of your choice, you have that the y, therefore the base will now take up the power, will now take the variable that you created as a power. That becomes 3 raised to power y, which is equals to 9. And by comparison, the value for y is equals to 2. So that is that for that example. Now example b. Example b is 5 log 8 base a minus 2 log 9 base a. Are you getting it? Now, provided that since they have the same base, you don't have a problem. You can use the normal application of logarithm, right? Division, when you see multiplication, when you see, sorry, the first one is log 9 base 3 plus log 10 base 3 minus log 6 base 3. So when you see addition, the first thing that comes to your mind is multiplication. When you see division, when you see subtraction, the first thing that comes to your mind is division. So 9 times 10, 90 divided by 6, which is 15 base 3. That's the first part. The second one is 5 log 8 base a minus 2 log a base 9. So we took the 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 power, we took the 5 back to its original position, and we have log 8 raised to power 5 base a minus 9 raised to power 2 base a. And division, subtraction is there, so you divide both sides, and we have our final answer as that. Now you can simplify this further because the base of the logarithm is base a, so it is not specific. Assuming that the base is not base a, or rather let's say that there is no base, you would have simplified this further by using your calculator or something. So that is that for the first part. Now, moving on to other questions. Now, this question, we are told to find the value for x for 500, 2.1 raised to power x equals to 50,000. So the first part, we divide both sides by 500, and we make x the subject of, we divide both sides by 500. When we divide both sides by 500, we will be left with 2.1 raised to power x equals to 100. Now, you now introduce logarithm to both sides. So by introducing logarithm to both sides, you'll be left with log 2.1 raised to power x equals to log 100. And by one of the rules of logarithm, you bring down the power, you take x down to the back side, and you divide both sides by log 2.1. And our final answer is 6.207. So that's the value for x. So you can use the same approach for the example b. Example b is 6 raised to power x equals to 3 multiplied by 5 raised to power x. Now whenever you have values like this, that logarithm is not there, and you are seeing that a number is taking up a variable as a power. I repeat, whenever you have a number that is taking up a variable as a power, what you do is that you introduce logarithm. Are you getting it? You introduce logarithm. So you are going to introduce logarithm to both the left hand side and both the right hand side, such that you will have log 6 raised to power x is equals to log 3 multiplied by 5 raised to power x. Now, there is something common. When you take the logarithm of both sides, you'll be seeing that you notice that 3 is multiplying 5 raised to power x, and in the rules of logarithm, multiplication is the same thing as addition. So you are going to split the 3 and 5 raised to power x by introducing an addition sign, because you initially introduced logarithm. So therefore you have log 3 plus log 5 raised to power x, and you know vividly that when you have log 5 raised to power x, the next thing that comes to your mind is to bring the power down to the back of the logarithm. So you have x log 5. Similarly to the left hand side too, you have x log 6, and you equate it. Now there is a common relationship between the left hand side and the right hand side. Those places that have x, you take collect like terms and you factorize out the value for x. So by factorizing out the value for x, you have x outside log 6 minus log 5. And log 6 minus log 5, you notice that there is no base. If you see a logarithm that the base is not indicated, what comes to your mind is that you assume that they have the same base, or they are in base 10. Are you getting it? So 6 minus 5 is still the same thing as 6 over 5. So you make x the subject of the formula such that you have log 3 over log 6 divided by 5, which is approximately 6.025. So this is everything for chapter 4 for logarithm. So you can, I intentionally added this exercise there. It's part of the exercise, but we solved all of the exercises. So if you want to have access to all of the exercise, a well-detailed solutions and answers for all of the exercise, as I mentioned earlier, I'll be dropping the number in the comment section so you can have access to them. Thank you. So we've now moved to chapter 5, which is sequence and series. Now, there is a misconception about sequence and series. Now, sequence is a different phenomenon, while series is an entirely different phenomenon. Entirely. Though during your early stage, when you were coming across this course, when you first heard of sequence and series, most students usually join the two of them together as though they are the same thing. Sequence is highly and far different from series. So we'll be taking them one after the other. So we take sequence first. What is sequence? A sequence is a set of numbers in a well-arranged order. In a well-arranged order, in the sense that you have 2, 4, 6, 8, 10. You have 1, 3, 5, 7,
10, and so on. You see, there's a reoccurrence, there's a pattern, there's a difference, there's a relationship between these values. So you can call this as sequence. So look at this number very well. You notice that the sequence or the difference of this number is 2. So because the difference is 2, we can come to a general conclusion and say that the general term is going to be 2r. What is the r there for? The r is representing a real value or a real number system or a real number. Are you getting me? Now, the real number that we have, real numbers start from minus infinity to positive infinity, which is indicative of the fact that there is an inclusion of 0, minus 3, minus 1, minus 3, minus 2, minus 1, 0, 1, 2, 3, and so on. So if you say it is equals to 2r, when r is equals to 1, you have 2 times r, which is 2. When r is equals to 2, you have 2 times 2, which is 4. When r is equals to 3, you have 2 times 3, which is 6. When r equals to 4, you have 2 times 4, which is 8. When r equals to 5, you have 2 times 5, which is equals to 10. So that is the reason why you have the general term to be like that. So in some cases, you'll be asked to look for the general term of a sequence. So by the time you discover the difference and you discover a reoccurring pattern, that is when you'll be able to conclude about the general term of a given sequence. So have that in mind. Now, still on general term, the examples we have here says that we should find the general term UR for the following. Now, there are some sequence that it is very easy to note or to understand their differences. Now, for this one, if you see 1, the next thing you have is minus 2, the next one you have is 3, the next one you have is minus 4, next one 5, the next one is 6. Now, the first thing that comes to your mind is that there is a reoccurrence, there is a jumping of values. I mean, there is a positive, negative, positive, negative, positive, negative. Whenever you come across situations like this, the first thing to do if you are asked to find the general term is to write out minus 1 raised to power r plus 1. Are you getting it? The first thing that you should do is write minus 1 raised to power r plus 1. That is the general term for a repeated values. I mean, repeated signs or changing signs. So whenever you have minus, positive, minus, negative, positive, that whenever you have values that have negative, positive, negative, positive, the first thing that comes to your mind in order to generalize it is you must introduce minus 1 raised to power r plus 1. That's when you have skipping signs like that. Now the next thing that you have to introduce is the value for r. So the value for r there, the r there that you have represent real number, and as I already stated earlier, real numbers can be any values 1, 2, 3, 4, 5. So that's why you have the general term for that to be minus 1 r plus 1 multiply by r. Now the other part that you have, the next thing that you have is you have minus 1 1 minus 1 1 minus 1 1 minus 1 1. Are you getting it? Now this other one that you have, you see that they also have the same uh pattern like the first one, but the only difference is that the numbers are just single values. So because the numbers are just single values, you are going to generalize it as minus 1 raised to power r. Are you getting it? So if you check now, you can always confirm or check if what you've generalized is correct or not by introducing the values for r. So for example, the second one, minus 1 raised to power r, when r is equals to 1, you have minus 1 raised to power 1, which is minus 1. When r is equals to 2, you have minus 1 raised to power 2. Minus 1 raised to power 2 is 1. Are you getting? When r is equals to 3, you have minus 1 raised to power 3. Minus 1 raised to power 3 is minus 1, and so on like that. Now the next one, the last one that we have is 1 over 4, 1 over 9, 1 over 16, and so on. Are you getting it? Now you are going to discover that there is a pattern. We have 1 over 4, 1 over 9, 1 over 16, and the first thing that comes to your mind, look at 4, look at 9, look at 16. The next thing you have is recursive sequence. Now the recursive sequence is that when you have first two terms, now the first term is called u1, the second term is called u2. Now the formula or the rule of the recursive sequence is that you have 3 multiplied by ur minus 1 plus ur minus 2. Don't worry, you'll get to understand this as time goes on. Now don't forget that we have the first two terms. For every recursive sequence, the first two terms are always given or they are always known. Are you getting it? The first two sequences are always given or they are always known. So without the first two sequence given, you cannot find a recursive sequence. Now by the application of this particular rule, if u1 is equals to 1 and u2 is equals to 5, right? Now this simply means that by the application of the formula 3ur minus 1 subscript r minus 1 plus ur minus 2, if you want to find u3 will be 3 times ur minus 1. Ur minus 1 means that when r is equals to 3. Are you getting it? So when r is equals to 3, you'll be having ur3 minus 2 plus ur3 minus 1. for u3, we want to find u3 now. U3 means when r is equals to 3. So anywhere you see r, you are going to substitute 3 in the rule. Anywhere you see r, you are going to substitute 3 in the rule. So you have u3 is equals to 3 multiplied by u3 minus 1 plus u3 minus 2. What is u3 minus 1? u3 minus 1 is u2. What's u2 minus u3 minus 2? u3 minus 2 is u1. So, and we are already giving u2 to be 5 and u1 to be 1. So you just substitute the values. That will be 3 times 5 plus 1, which is 16. That is u3. Now moving down to u4. The reason why it is called recursive sequence is because you are going to use the former sequence that you have to get the future sequence. You'll be using the former ones to get the future ones. So u4 now will be 3 multiplied by 16, which is u3, plus 5. Are you getting it? That's 53. The same thing for u5 too. u5 will be 3 multiplied by 53 plus 16, which is 175. The same thing for u6 too. 3 multiplied by 175 plus 53, which is 578. So it means that the first 7 terms for this particular recursive sequence is 1, 5, 16 down to 1909. So this is what we have by recursive sequence. So for recursive sequence, you can be given any formula of your choice, and you'll be given the first and the second term. Then they will ask you to find the remaining terms. So that is all for recursive sequence, and that is everything we'll be talking about when it comes to sequence. Though there are still some other parts we'll still touch, but we are moving down to series now. So as I said earlier, there is a huge difference between series and sequence. Now, when you hear series means that you are going to add all of the terms of a sequence. So the addition of all of the terms that you have in a sequence is what we refer to as series. So when we say sequence, for example, 2, 4, 6, 8, 10, this is a sequence. But when do a sequence becomes a series? A sequence becomes is when all of the additions, when all of the sequence are being added. So we usually represent it with a summation symbol. So if you have 2, 4, 6, 8, 10 as a sequence, the series will now be 2 plus 4 plus 6 plus 10. So you are going to introduce an addition sign instead of a comma sign. So when immediately an addition sign is being introduced, then it becomes a series. Are you getting it? And most times we usually represent it with a summation symbol. So you can see it as summation UR. So summation UR is U1, U2 up to UN. So that's a series. Are you getting it? Now, so moving down to example 5.4. Example 5.4 says that the sum of the first and tenth of a series is given by the formula n squared minus 4n plus 1 for every value of n. So we are asked to find an expression for the rth term of the series. That's the position, the rth term of the series. Now, what you are going to do whenever you come across a situation like this, you are given a particular series. You are given, whenever you are given a general formula for a series and they want you to find an expression for the rth term for the series, what you are going to do is that you must take note of the term itself. Then you are going to subtract it from 1 minus the term. That is, UR will therefore be SR minus 1. It is a standard formula. So you don't need to ask me where is that formula coming from. That's the standard formula for finding the rth term of a series. Are you getting me? So for UR, XR is going to be U1 plus U2 plus U3 up to UR. Are you getting me? Then you are going to subtract it from that same U1, U2, U3, but it will now be the last term is going to be UR minus 1. The reason we are doing this is because we are following the pattern UR equals to SR minus 1. Are you getting me? So all the first U1 in the first bracket, they are for SR. The second U1 down to UR minus 1, they are for SR minus 1. Are you getting it? Such that anywhere you see U1 is still representing n squared minus 4n plus 1. So instead of us using n now, we are now using UR. Are you getting it? Because the question says that find an expression for the rth term. So that's why we are introducing r. Don't forget we have n squared minus 4n plus 1. So if you are introducing r now, it's going to be r squared minus 4r plus 1. So that's going to be for the first part. Now for the second part, what we did is that we factorize out the value for r such that, you see, if you open r minus 1 squared minus 4r minus 1 plus 1, that part that we have now is anywhere you see r, you are going to put it as r minus 1. Are you getting me? Anywhere you see r, you put it as r minus 1. It is no longer r. So don't forget we are dealing with ur and ur minus 1. The first one is for the natural value for r. The second one is for the values. One is taken away from r. So that's r minus 1 squared minus 4r minus 1 plus 1. So the next thing is just to simplify. You expand the bracket. By expansion, you have r squared minus 2r plus 1 minus 4r plus 4 plus 1. We've expanded. And when you expand and simplify, you have the rth term to be 2r minus 5. So that is how to find it. So take note of this. You can be given any formula of your choice. Not necessarily n squared minus 4n plus 1. You can be given n squared plus 7. Are you getting it? And they will ask you to find the rth term. So if you ask to find the rth term, it simply means that you are going to find for r, then you find for r minus 1. Then you now use it in xr minus 1. So it's very simple and it's very straightforward. So that's that for that particular example. Now moving down to example 5.5. Example 5.5 is also a series. Whenever you see a summation symbol, the first thing that comes to your mind is series. You are not doing sequence again. I get him. Now the summation symbol represents r squared plus 2r. It is given, and they told us that r is going to be from 1 and it will terminate or it will stop at 4. That's what it means. So you are going to substitute the value for r starting from 1, and you are going to end it at 4. So you have 1 square plus 2 times 1. That's the first one. The second one, 2 raised to power 2 plus 2 times 2. That's the second one. The third one, 3 raised to power 2 plus 2 times 3. That's the third one. And the last one is going to be, you are stopping at 4. So whenever you see a summation symbol, for example, if I give you summation of r equals to 1 to 7, it means that I'm asking you to stop at 7. Are you getting it? So that is that. And when you do everything and you add, when you simplify everything and you add them together, our answer is equals to 50. And the second one, 2 raised to power r minus 1, r ranges from 2 is equals to 5. And you can see clearly now that this second one, the r is starting from 2 and is going to end at 5. So you see, we start from 2 raised to power r minus 1. R minus 1 means 2 minus 1. 2 minus 1, that's 1. The second one, 2 minus, the second one is 3. Are you getting me? When r is equals to 3, that's 2 raised to power 3 minus 1. 3 minus 1 is 2, and so on. And by simplification, we have our answer to be what? 30. So that's that for all the examples. Now, moving down to the last part, which is arithmetic sequence and series. Now, it is this arithmetic sequence and series that you did when you during your secondary school days. So that is, it is called arithmetic series and sequence. That's arithmetic progression and geometric progression. Arithmetic progression and geometric progression is different from sequence and series. Are you getting me? They are two different things. They are different from sequence and series. The word arithmetic is already introduced, right? So if the difference between two consecutive terms of a sequence is a constant value, you have a plus d, a plus 2d, a plus 3d. So all these ones are arithmetic progression or arithmetic sequence. So take note of the difference. You don't need to confuse one for the other. So now, we have introduction to progressions. As I said earlier, a sequence is an ordered list of numbers. A progression is a sequence with specific pattern. A progression is a sequence with specific pattern, while a sequence is an ordered list of numbers. So that was why I told you that there's a difference between a sequence and arithmetic progression. There's a difference between AP, arithmetic progression, and sequence. So we have sequence, we have series, we have arithmetic progression, we have geometric progression. All of these things, they are 4 different things. They are not the same thing. Some students usually confuse arithmetic progression with sequence. They say, if you ask them, what do you do? They will tell you they did sequence and series, which is the same thing as arithmetic progression and geometric progression. They are 2 different things. So you don't confuse the two for the order. So arithmetic, that's progression, and that's sequence. Are you getting it? So let's move down to AP, which you are already familiar with. So we have the first term, we have the common difference, we have the number of terms. Are you getting it? So the number of terms, example 2, 5, 8, 11, 14 is an AP. The reason why it is an AP is because the common difference, there is a common difference, right? There is a specific pattern. That is why it is called progression. There's a specific pattern, which is 3, which is common difference, and the first term is A, right? So that is that. Then down to sum of arithmetic progression. I already proved it, though you will not. Nobody asks you to prove this because you are writing a computer-based test, right? So nobody will ask you to prove it, but you just need to know the similarities. So we have sum of AP, and I believe that most of us would have seen something related to this. So you can skip the proving part. So, but if you still want to study the proving, it is fine. And the sum of AP is given as n over 2, 2a plus n minus 1d, right? Which is still the same thing as n over 2, a plus last term. A plus last term. So that is it. So it means that what we are saying here is that last term that they are referring to is this. The formula for last term is a plus n minus 1 close bracket d. That's the formula for last term. So you notice that if you add the first a and the second a, is going to become 2a, which you go back to the second formula. So that's, is either you write it as the first one or you write it as the second one. It's still the same thing, right? So let's take a few examples. Now this example says, now mind you, these are the type of questions you'll be seeing under AP, not just like the secondary school method that you've been using. So the question says, find the three different numbers in AP whose sum is 15 and their product is 84. Now 3 different numbers. Now the numbers are unknown, we don't know them. Now whenever I come across situations like this, what you are going to do is that you are going to pick 3 different variables from an arithmetic sequence, and the major ones that we usually pick, they are a minus d, a, and a plus d. And the questions already stated that their sum is 15. So it means that when you add all of them together, you are going to get 15. And by addition, you will notice that automatically all of the d that we have in the variables that we pick cancels out, and we find a, which is the first term. So by finding a, which is the first term, we made a subject of the formula, and a is equals to 5. So should, in case you want to find the difference, but we are not asked to find the difference, okay, we'll definitely find the difference. So by introducing the value for a back to what we already have initially, we are going to take the product, right? Because they told us that the sum is 15 and their product is 84. We've added everything together and we have 15. Now we are going to multiply it. By multiplication, we already have 5. So we have 5 minus d multiplied by 5 plus d. And by simplification, we have 125 minus 5d squared is equals to 84. And when we made d the subject of the formula, we had d to be plus or minus square root of 205 divided by 5. So we have d. Now since we have d, and they want us to find 3 different numbers, we have a, we have d. So you go back to the question, the 3 numbers that you pick, and you substitute the values there. So by substituting the values back, the three numbers that we now choose are now 5 minus square root of 205 over 5, 5, and the last one 5 plus square root of 205 over 5. So that's that for the last part. Then we have geometric progression. Geometric progression is an arithmetic sequence where each term after the first term is obtained by multiplying by a constant ratio. You see, geometric progression is we have common ratio. Geometric arithmetic progression we have common difference. Are you getting it? So and you can see that's the general formula. Then we have the sum of GP2. So you can skip the proving, but if you want to go through the proving, it's fine, no problem. So for the general form of a sequence of the sum of a GP is a1 minus r raised to power n over 1 minus r. Alternatively, now there are conditions for this. I didn't state the conditions. Now the first condition, okay, I already stated the condition. The condition is that r is not equals to 1. You know, if r is equals to 1, it means that that sequence is going to be 0, because 1 minus 1 is 0. So the denominator will become 0, and you have anything over 0 becomes infinity. Sorry, the sequence will become infinity, I mean. Are you getting it? So that's the condition for the two form of the sum of a GP. So know the formula, know it, because nobody will definitely ask you to prove. So know it, because you're writing a CBT exam, you must know it, and you must know how to apply them when you see questions. So special cases, the special case is as a result of the nth term for the infinite term of a GP, or yeah, of a GP. So sum to infinity. So some people call it sum to infinity. Are you getting it? So the condition is that when r is equals to 1, all the terms are equal. So there's a condition, you must take note of that. When r is equals to 10, it means that the first term will be equals to second term, will be equals to third term, will be equals to fourth term, and so on. So you can see questions like this: which of the following is correct when the value of r is equals to 1? So all the terms of a geometric progression is always equals to 1. They are always equal when r is equals to 1. Okay, that's that for that. So we have an example quickly, and we have to find the sum to infinity. Sum to infinity means that the last term. So sum to infinity means the last term. So a is the first term, which is 1. R is the common ratio. What is the common ratio here? You are going to, the common ratio is the second term divided by the first term. Are you getting it? The common ratio is the first term, second term divided by first term, and 1 over 2 divided by 1 is still the same thing as 1 over 2. So if we put it, we have 1 over 1 minus 2. 1 minus 1 over 2 is still 1 over 2. Are you getting it? So by simplification, the sum to infinity for this very question is equals to 2. So this you can check out the applications, and you can check out the summary. So this is where we stop for chapter 4 and chapter 5 of Maths 110 manual. So if you have any question, you can just drop them. But this is where we'll stop. So I'll be uploading the other chapters as time goes on. Thank you.